Okay, no one's waiting to join, so I'm going to go ahead and get started. Okay. So in the chapter we've been looking at, we've looked at the reactions of alkenes and alkynes. On the previous chapter, we looked at one unique reaction of alkynes, and that involved using a terminal alkyne, in which we do an acid-base reaction. And as we'll see later, this can also be used to alkylate or extend the chain of an alkyne. Okay, so if we have say something like bromoethane, okay, we can add 2 more carbons to the chain. Okay, this has to be a primary halide. That is, this carbon is only bonded to one other carbon. Otherwise, this won't work. If we have an alkyne which is not a terminal alkyne, say something like 2-butyne, and there'd be no reaction in R. Nothing would happen. Okay, these hydrogens are not acidic. Okay, in the chapter that we've just been covering, most of the reactions involve addition. And the reactions of alkenes and alkynes were similar. Okay, if we have an unsymmetric alkene, we can add a hydrogen halide, HCl, HBr, or HI, not HF since that's a weak acid. We have something like HCl. H and Cl, it adds to the double bond, and this is a regioselective reaction. Okay, we get one positional isomer in preference to the other. And the way this works, okay, H will add to carbon number 1 because that will give us the more stable secondary carbocation. If H added here, our plus charge would be here, which would be a primary. All right, electrons move toward chlorine, so now it's negative. And remember, electrons are negative. Then opposite charges attract. Okay, we always draw arrows from negative to positive, and so our product would be 2-chloropropane in this case. Okay, here I have 1 butene. Okay, this is the acid catalyzed hydration. Okay, we add H and OH. And this follows Markovnikov's rule as well. Okay, this side has 2 hydrogens, this side has 1. So the hydrogen will go to carbon number 1, plus charge goes to number 2, and our product will be 2-butanol. Okay, so this one is also regioselective.
So does that reaction just happen in H3O? Or what is the H3O?
Okay, when you mix, okay, the question was, what's the H3O? You take a strong acid like sulfuric acid, and sulfuric acid completely ionizes. And so this is carried out in 10 to 20% sulfuric acid. And so every sulfuric acid is going to protonate a water molecule. So that's where you get the H3O. Okay, we also talked about addition of halogens, chlorine and bromine. Okay, so here we have cyclohexene. These carbons have a trigonal planar geometry. Okay, we can do this with chlorine or bromine. You could also do it with iodine, with heat, but mainly we talked about chlorine and bromine. So what happens here is that the alkene will attack one of the bromines. And then we'll form a 3-membered ring. Okay, the 6-membered and this 3-membered ring are folded. Okay, this is forward or it could be back. And then the hydrogens are back. All right, bromide, which is produced in this step. Okay, bromide has to attack from the back side. Okay, which in 3 dimensions would be behind the board, this way. Okay, and that is going to cause this ring to break open. Right, and that means that okay, so this bromide will attack from the back side. That's going to push this hydrogen forward when that happens. Okay, the configuration is this carbon won't change. Hydrogen will still be back. This bromine will still be forward. Okay, we broke this bond right here. Okay, this mechanism explains why you only get the trans. Okay, you don't get a cis, you don't get a mixture of cis and trans. If this ring did not close, then we would indeed get a mixture of cis and trans, but we only get the trans. Okay, so this is an example of a stereo selective reaction. Okay, prefers a particular stereoisomer, namely the trans. All right. We talked about a couple of others. One was this one called hydroboration oxidation. Okay, this occurs in two steps. The product or intermediate in this first step is not isolated. Once this first reaction is done, then we add hydrogen peroxide and hydroxide. This gives us an alcohol. Okay, but this is a situation in which the poor get richer. Okay, the Robin Hood reaction. Okay, unlike acid catalyzed hydration. Okay, the reason we compare borane with, say, hydronium. In hydronium, hydrogen is electron deficient. Okay, it carries a high positive charge. It's just the opposite situation with borane. Okay, boron is more electronegative than hydrogen is more electronegative than boron. And so these hydrogens are electron rich instead of electron poor, so it's the opposite situation. Also, boron does not have an octet, which means it's a very good electron pair acceptor. By accepting a pair of electrons, say from a double bond, it acquires an octet. All right, we also talked about hydrogenation. We use hydrogen gas and a catalyst, usually nickel, palladium, or platinum. This adds hydrogen. Let's make this 1,2-dimethyl. Okay, this reaction is also stereoselective. Okay, we get mostly cis. Mostly cis. Okay, both the alkene and the hydrogen are absorbed at the surface of the metal, and the hydrogens are added one at a time. Once in a while, the alkene, after it adds a hydrogen, once in a while it rolls over, and the hydrogen adds to the other side. But you get usually about 85% cis. Reactions of alkynes are similar. Mostly addition. Okay, we can add HCl or HBr to an alkyne. If it's a terminal alkyne, then Markovnikov's rule is observed. HBr Okay, we can add one or two equivalents of HBr. Okay, we can also add HBr to this. Okay, again, the side that's richer in hydrogen would get the hydrogen. All right, we can also hydrogenate alkynes. If we use hydrogen and a catalyst such as nickel, palladium, or platinum, it's very difficult to stop at just one hydrogenation. Okay, usually it'll just go all the way to the alkane. We've added 2 hydrogens to each side, and we end up with a single bond. If you use a deficient amount of hydrogen, say just one equivalent, you're going to get some unreacted alkyne. Some of it will go all the way to alkane. Okay, what if we want to add just one equivalent? Well, then we can use what's called the Lindlar catalyst. Okay, using hydrogen and the Lindlar catalyst. The Lindlar catalyst is you take finely powdered palladium, and then it's been diluted and partially deactivated so that it's not as efficient. Okay, and this reaction is also stereoselective. You only get the cis alkene. Okay, both hydrogens are added to the same side. And it stops at just one hydrogenation. Okay, so what we'll do next is we'll move on to the next chapter. And I'll share my screen in just a moment here. Whoops. Okay, so this would be chapter 6. Okay, we're going to begin a new topic. Okay, and I will share my screen. Okay. Okay, this is the topic of what is called chirality. Chirality means handedness. Here's a general table of isomers. Okay, up at the top we have all isomers. Okay, over here we have constitutional isomers. There's a number of different kinds of constitutional isomers. We can change the carbon skeleton. We can change the way in which the carbon atoms are connected. Okay, but isomers have to have the same molecular formula. Okay, so pentane and cyclopentane are not isomers because they have a different formula. Okay, and then we've had some introduction to cis-trans isomers. Okay, those are a type of stereoisomer. Okay, down here, we've got cis and trans. These are not constitutional because if we look at these two variations of 1,2-dimethyl cyclohexane, they're both 1,2-dimethyl cyclohexanes. Okay, skeleton is the same, but the three-dimensional shape is different. Okay, and we're going to introduce these other terms shortly, enantiomers and diastereomers. Okay, those are both types of stereoisomers. Okay, cis and trans alkenes are stereoisomers, and they're also what are called diastereomers. And we'll define the distinction here between enantiomers and diastereomers. All right. Definition of enantiomers is that they are non-superimposable mirror images. Okay, this is 2-butanol. Okay, we haven't really learned how to name alcohols yet, but butane, 4 carbons, all is the suffix for alcohol, and that's on 2. And it turns out that there are 2 mirror images of this that are not superimposable. That means we can distinguish between the 2. We cannot lay them on top of each other and line up all the bonds at the same time. Okay, if we take the one way to see that the mirror image of the 2-butanol is not superimposable on the original is to rotate the mirror image, then compare it with the original. Okay, if this is the original, this is the mirror image, and okay, what you'll see, for example, we've rotated it 180 degrees in this direction. Okay, while methyl and OH are in the same position, okay, notice that the ethyl and the hydrogen are switched. Okay, and it is not possible to line up all 4 of those groups at the same time. Okay, so the original and its mirror image are not superimposable. And these are actually different molecules with different properties. Okay. Enantiomers are stereoisomers that are non-superimposable mirror images. They're chiral, which means they have this property of handedness. And this term refers to the relationship between pairs of objects. The most common cause of enantiomerism in organic molecules is the presence of a carbon with 4 different groups bonded to it. And that carbon with 4 different groups is called a stereocenter. It's also called a chiral center. I'll use the terms interchangeable, stereocenter and chiral center. Okay, so look for 4 different groups bonded to a carbon atom. Now, carbon is not the only element that can exhibit chirality. Okay, other elements, for example, in the same family, like silicon and germanium, if you have 4 different groups bonded, they can exhibit this property of chirality. All right, many macroscopic objects possess this property of chirality. Okay, chirality, handedness, your hands. Okay, your right hand and your left hand are mirror images of each other. Gloves. You have right-handed and left-handed gloves. And if I have a box of gloves, we can easily pick out which is which. These are mirror images of each other. Okay, shoes. You have right and left shoes. Cars, for example. Okay, what would the mirror image of most of these cars out here look like? What would be one main feature? Okay, the steering wheel will be on the other side, right? Be on the right instead of the left. These writing desks over here, these are right-handed. The mirror image would have a left-handed. Screws and bolts have a property of handedness. Most screws and bolts have what we call right-handed threads. Okay, righty-tighty, lefty-loosey. You tighten it by turning it to the right or clockwise. A few years ago, I had to replace a flush lever on a toilet, and I couldn't figure out why I had such a hard time getting the old bolt off. And I struggled and finally broke the bolt. Went to the hardware store, got a new one, and turned out it had left-handed threads. There were also some cars, Chrysler, Plymouth, Dodge cars around 1970 that had left-handed lug nuts on their wheels. Okay, if an object and its mirror image are superimposable, they are identical, and there is no possibility of enantiomerism. All right, such an object is what we call achiral, which means not chiral. Okay, consider 2-propanol. Okay, notice the difference here between 2-butanol, which is right here. 2-butanol has 4 different groups. It's got the OH, methyl, ethyl, and hydrogen. So it's 4 different groups. Propanol, 2-propanol, has 2 groups that are the same, these 2 methyl groups. And so it and its mirror image are identical. Okay, there's no stereocenter, and so you can't tell the difference between the 2 mirror images. Okay, so this is an achiral molecule. It has no handedness. Okay, so to summarize, an object that is non-superimposable on its mirror image is chiral, that is, it shows handedness. The most common cause of chirality among organic molecules is the presence of a carbon with 4 different groups bonded to it. Okay, and that actually rules out double and triple bonds, because if you have a double bond, you have 2 bonds to the same thing, so that cannot be a stereocenter. A carbon with 4 different groups bonded to it is called a stereocenter. Okay, an object that doesn't possess this property is called achiral. Enantiomers, like gloves, always come in pairs. Okay, so these are different representations of 2-butanol. Okay, the point here of this slide is that in this last representation, okay, there is a hydrogen here that's implied that's going back. Okay, it has to go back because of the tetrahedral shape. Okay, so this is a more accurate representation of the line angle formula. Okay, you can't have both these groups coming forward. Okay, something else I want to mention. And that is if we have a dash and a wedge, like this, the dash and the wedge always have to be on, you always have to draw those on the same side of two solid lines. Okay, so this is correct. This is not. Okay, don't draw your structures like this. Okay, these have to be on the same side. Okay, and it's very easy to convert that to its enantiomer. Okay, all you have to do is switch two groups. Okay, you can switch either the methyl and the ethyl, or you can switch these two. Okay, so I could bring the OH back and the hydrogen forward. You never want to draw two dashes or two wedges because that's impossible, and we can prove that using models. Okay, the angles would be prohibitive. Okay, so how do we distinguish between the two? Okay, so this is how we draw the molecules to represent their three-dimensional shape. Okay, in this case, these would be the same because we switched both the H and the OH, and we switched the methyl and the ethyl. So these are actually the same molecule. All right. Here is but one example of a chiral compound. This is ibuprofen, okay, the active ingredient in Advil and Motrin. Okay, these are two mirror images, non-superimposable mirror images. And it turns out this is the active isomer. Okay, and then this other one is inactive. I'm sorry, this one's inactive. I read that wrong. This is inactive, this one is active. Okay, so how do we tell? We use something called the R&S system. Okay, you may remember when we were talking about alkenes that there was the E and Z method of designating geometric isomers, and we established priorities based on atomic number. Okay, well, we use the same rules except that we prioritize all four substituents. Okay, so we'll assign a priority from 1 to 4 to each group on the stereocenter. Okay, and then point number 2 is important. You need to orient the stereocenter so that the group of lowest priority is away from you or back. Okay, and then we'll observe the order of the other three groups that are projecting toward you. And if those are arranged in a clockwise pattern, then this is the R. And that's from a Latin word meaning straight or correct. If the groups are arranged in a counterclockwise or to the left, that's called S, which comes from the Latin sinister, for left. All right, so here we have 2-chlorobutane. And we want to orient this so that the lowest priority group is away. Okay, so we have directly, this is our stereo center on carbon number 2. Okay, so we have 4 different groups. We have a chlorine, a hydrogen, a carbon, and a carbon. Okay. Chlorine is obviously highest priority. It's atomic number 17. Carbon is 6, and hydrogen is 1. So hydrogen is obviously last. Okay. And here we have a tie. These are both carbons. But the next one out on the methyl would be a hydrogen versus on the ethyl it would be a carbon. So carbon beats hydrogen. Methyl loses out to ethyl. Okay, and then we direct it so that the lowest group, hydrogen, is away from us. And the other 3 groups, chlorine, ethyl, methyl, that's in a counterclockwise formation, so this would be S. 1, 2, 3, that's counterclockwise, so this is S. Right, down at the bottom we have another example. And this is our stereo center. Got 4 different groups. Okay, so OH is 1, hydrogen is another. These are both carbons, but the alkene is clearly different from the alkane, so these are 2 different groups. So oxygen is atomic number 8 versus carbon, which is 6. So oxygen is number 1. Okay, we orient, we rotate the molecule so that the lowest group is away from us. Hydrogen is last. Okay, so we've got carbon and carbon. Okay, for a carbon-carbon double bond, okay, remember we treat that as though we're bonded to 2 carbons. Okay, so 2 carbons and a hydrogen beats out 1 carbon and 2 hydrogens. Okay, so the alkene has higher priority. Okay, so it goes like this, 1, 2, 3, this is clockwise or R. In most of the examples, the lowest priority group is a hydrogen, but it doesn't have to be a hydrogen. In fact, if we had a methyl instead of a hydrogen, methyl would be the lowest priority, but it has to be away from you. Okay, because this is my right, but it's your left. Okay, if I make circles this way, that looks clockwise to me, but it looks counterclockwise to you. So the direction in which you view the molecule is important. Okay, so here's ibuprofen again. And the inactive isomer has the R configuration. The active enantiomer has the S. Okay, priorities are the same in these. Okay, so we've got carbon, 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 and hydrogen. Okay, hydrogen's last. This carbon is next to the last because the next atom out is a hydrogen. Okay, and then it's between 2 carbons, one on the benzene ring, one here. Okay, but then we have a double bond to an oxygen and another oxygen. So oxygen is higher priority than carbon. Okay, so the carboxylic acid is highest priority. Okay, so it's carboxylic acid, benzene ring, methyl. Okay, and this is clockwise or R. Okay, and then to draw the enantiomer, all we have to do is switch 2 groups. Okay, so they've switched the carboxylic acid and the benzene ring. This is the S.
So S is always the more active one?
No. For ibuprofen it is. Yeah, it depends on the compound. Okay, many molecules have more than one stereocenter. And if you have just one stereocenter, which has been the case in all the examples so far, two stereoisomers are possible. If you have two stereocenters, then it's 2 to the second power, or 4 stereoisomers that are possible. Okay, so what that means is that each time we add a stereocenter, we'll double the number of possible stereoisomers. Okay. And so if we have 4 stereocenters, that would be 2 to the 4th power, or 16 possible stereoisomers. All right, so here's an example of a compound that has 2 stereocenters. Okay, this compound is called 2,3,4-trihydroxybutanal. Again, we haven't learned how to name those yet. But these are the 2 stereocenters. 4 different groups: OH, CH2OH, H, and then this whole group here. And then this also has 4 different groups. We got an alcohol, an aldehyde, a hydrogen, and then this group with the 2 alcohols. So there are 4 possible stereoisomers. Okay. And okay, here we have the original. Well, okay, let's call this the original molecule A, and its mirror image. Okay, these are not superimposable. Notice what we've done here. We have switched the configuration at both of these stereocenters. Okay, we've switched the H and the OH at both of these. If we switch the H and the OH at just one, okay, this one has a mirror image as well that is not superimposable. These are mirror images of each other. These are mirror images of each other, but this one and this one are not mirror images. Okay, so we've got 2 pairs of enantiomers from our 2 stereocenters. Okay, so B and C, for example, are related as diastereomers. Okay, and I'll have more to say about that next time. I'm going to go ahead and end here.